Okay, now we're going to talk about using niche models, distribution models in testing hypotheses about patterns of niche overlap and niche evolution. Right, we already talked about how we measure niche breadth, how we measure niche overlap. So we've got a pair of species, we build models for them, and then we have these metrics where we measure similarity between species, and then, essentially we want to ask, is that more or less similarity in niche models than we expect by chance? And for that, we need to have some idea of what we mean by chance, and that's where these Monte Carlo tests that I already sort of talked about come in. We basically use some randomization procedure to generate a distribution of expected overlaps under a given null hypothesis, right? So we figure out how to simulate what our data would look like if the null hypothesis were true. We do that a whole bunch of times, right? And then we use that to generate an approximation of the distribution of overlaps under that null expectation. And by comparing our empirical observation to that distribution of overlaps, we can reject or fail to reject a given null hypothesis. So that's kind of the broad Monte Carlo thing. So in terms of niche conservatism, the sort of reason for existence for E&M tools in the first place is a paper I did with Michael Torelli and Rich Glore in 2008, where we sort of looked at some existing niche conservatism studies, and we kind of noticed that they were testing different null hypotheses using the same name. And so we wanted to generate a sort of consistent statistical framework within which we could address all those hypotheses in the same framework and see what the relative support for them is. So the first hypothesis we identified was this thing called niche identity. That's what we called it. It's also been called equivalency. This was the hypothesis tested by Graham et al. In 2006. It was that this is one of those things, the literature was really confusing up to that point because the hypothesis tests were not necessarily that explicit in what they considered the definition of niche conservatism to be. So there was actually a lot of conflict in the literature, primarily driven by the fact that people were testing different hypotheses under the same name. So Graham et al. Did this paper on, if I remember correctly, dendrobatid frogs, where they did this statistical test that implicitly, I think, defined niche conservatism as something like this niche identity idea. The idea that closely related species are very, very similar over long periods of time, right? So, so if that were true, if closely related species were effectively ecologically identical or near enough to identical that they're more or less interchangeable, how can we actually simulate a null distribution to test that hypothesis? So we've got our two species here. They're occupying fairly similar environments, but how do we actually generate the null hypothesis, the distribution under that null hypothesis of niche identity? Well, if that hypothesis were true, then the environmental associations of those species would effectively be just different random draws from the same distribution. It doesn't mean that the data for the two species is identical. It means it's two random draws from the identical distribution, right? So you could have two sets of numbers drawn from the same normal distribution, and numbers aren't going to be the same, but the underlying distribution will be the same. And so we're essentially trying to simulate data under that kind of scenario where the underlying geographic and particularly ecological, more than geographic, distribution of our species is identical. So if that null hypothesis were true, then this scenario, our empirical scenario, would be, in terms of the environmental distributions of our species, kind of interchangeable within the overlap we see would be interchangeable with any scenario where we sort of randomly shuffled the identity of these individuals. So we keep the sample size for our two species identical, but we randomize the identity of the individual occurrences for our two species. So we randomize their identities. We measure overlap for every one of those replicates. And then we basically use that to build a distribution of expected overlaps between our two species under that hypothesis that they are drawn from the same underlying distribution of environments. And we typically find that even closely related species do not have environmental distributions that are fit within that null distribution proposed by the niche identity hypothesis. So this is a very commonly found finding, that species, even if they're closely related, are not occupying identical sets of environments. And so interpretation of that can be a little iffy. So often people want to interpret this as some signal of niche evolution. That's not necessarily a safe thing to do. First off, species can be very, very similar and still not be identical. So the larger your sample size, the finer, the more granular an environmental difference you're going to be able to see and detect as statistically significant, even if the actual differences are pretty minimal. Second, and I think more importantly, there's a potential for a strong bias here due to range overlap or a lack of range overlap. So you will often have species, that are allopatric, and they're allopatric for historical reasons, right? So it's possible that these two species used to be one species, and then there was some vicariance event that split it into, the orange species and the purple species. And it's when that happens, they occupy different environments because they occupy different areas. And of course, if local adaptation is perfect, eventually they will evolve to be different, probably, if there's a cost to high niche breadth. But the fact that they live in different environments doesn't necessarily mean they can tolerate different environments. And so in a scenario like this, where you have two species with identical fundamental niches occupying different regions, you will often find that the identity test or equivalency test says that they're much more different than expected by chance, but that's primarily driven by the differential availability of habitat and not necessarily a signal of underlying niche evolution. So, there's simulations that show that the niche identity test will reject the null hypothesis for allopatric species more often than not. Even when there's not, even if there's, under simulated circumstances, not an ecological difference between them. But we actually knew that going in. So in the same paper where we sort of developed this test, we also developed a test that attempted to correct for the different availability of background in the areas where these two species live. So we correct the availability by changing the way we do our sampling. So we correct for our environmental availability based on the way we do our sampling. So this is one of those things that makes Monte Carlo tests so powerful, is that the procedure is the same here, but by changing the way we sample our or simulate our occurrence data, we can actually change the hypothesis that we're addressing. So here we've got two species, the orange species and the purple species, and we can define a region for each of these species that delineates what we think is the set of environmental backgrounds or the space that they're actually able to sample. So we're saying, okay, maybe the orange frog can't get over here for dispersal reasons or whatever, and so the environments it has available to it are actually the ones that are within this oval range here. And maybe the purple frog can't actually get over here, and this is the range of environments or geographic regions that it's able to sample from. So what we do for this, to correct for the availability of environments in these two areas, is instead of randomizing the identity of our points, we actually will just shuffle around the location of our orange frogs within the orange frog range. And we shuffle around the location of our purple frogs within the purple frog range, keeping sample sizes constant and all that sort of stuff. And that gives us this baseline of the level of divergence we'd expect to see between two species with these two ranges, given their sample sizes, if the only differences between them were basically driven by the differential availability of habitat in the areas where they live, right? And so we just kind of randomly select points from the orange frog's range. We build models for those. We compare them to a model for the purple frog. And then we sort of do it in the opposite direction. So the way we originally proposed this was this asymmetric test where we randomize one species and then another. You can also randomize both at once. And that's actually implemented in ENM tools. And I actually kind of like that idea better. That was my original proposal. Michael and Rich sort of talked me out of it on the idea that, like, if there's some asymmetry there, where like the empirical overlap we see is outside of the range expected given, or the overlaps we'd expect given this species range, but not this species range, that we would be able to interpret that as some sort of biologically meaningful thing. But honestly, I think a good interpretation that's really reliable for that asymmetry just has never really materialized. So I kind of prefer the symmetric version now, where we sort of randomize both the species locations at once, and that is implemented in the R version of ENM tool. So, right, so this allows us to essentially build a distribution of expected overlaps under the null hypothesis that the differences between two species are simply due to allopatry, which I think is arguably a much more biologically meaningful hypothesis to test than that species identity test, right? Okay, so we initially did all of these tests in the context of measuring overlap between species distribution models in geographic space. But as I sort of talked about in the overlap section, there are kind of limits to the interpretation of that. We can now, in ENM tools, do the same tests using those overlaps in environment space that I talked about. But even before we sort of put out those environment space metrics for niche and distribution models, there actually was a sort of environment space alternative, and is an environment space alternative, called Ecospat. So Ecospat, this comes out of some work by Broennimann et al. In 2012. It's a pretty neat idea. A lot of people like to think of it as being model free. I don't think that's actually quite fair, but yeah, it's a pretty intuitive model. Basically, the idea here is that your species, got a little frog here, it has an occurrence with respect to an environmental gradient. So let's say this is temperature. Our species lives mostly in fairly cold areas, a little bit in warm areas, and then not very much at all in the super hot areas. So the idea behind Ecospat, how it parameterizes the niche, is to say that that occurrence is a product of the availability of that along that environmental gradient, the availability of habitat at those different temperature levels, times the species' environmental preference. So the species is going to sort of fill up all the available cold habitat and some of this warm habitat. So even though there's a lot of warm habitat, it's kind of relatively rare there. And then it's still going to just completely avoid the hot habitat. So the idea is that this purple thing here, the occurrence of the species, is the product of these two distributions. And you can do the very simple math then that says that if the presence of our species is the product of these two things, then this, you can call this fundamental niche or some sort of preference function or whatever you want to call it, but you could get this out, which is the niche that we're interested in, or at least something like it. You could get this out just by dividing the occurrence of your species by the availability of different values along that environmental gradient. So that's kind of the idea. You get your niche estimate by dividing your occurrence, and in this case it's in environment space, by the availability in environment space. And this is a really cool idea. So I like Ecospat a lot. I think the implementation can be quite challenging for someone who's not a very skilled R user to implement. And so for ENM tools, we've made a kind of simple front end on the Ecospat that uses all the underlying Ecospat code, but uses our ENM tool species objects and makes it a lot easier to use. So it is worth saying that if you're doing Ecospat tests, which again I think are very cool, it's worth visualizing the niche estimates that come out of them, because they are subject to a specific methodological error that is easy to detect if you visualize it, and not necessarily easy to detect just from the numbers. So they've done a lot in the past few years to actually, I think, make the defaults on this better, so you don't see this behavior as often, but still it's worth looking for. So what happens here is you've got some environment space here, right? So this is for a species, Anolis chlorocyanus. Anyway, you've got your species here, you've got the available environment in its region, and then you've got its actual occurrence. And then you've got your niche estimate, which again is just this divided by this. What do you notice about this niche estimate that's really weird? Well, all the best habitat or best environments, as far as this niche estimate is concerned, are along this ridge here. That's kind of weird, right? Yeah, it's saying there's this ratio of axis 1 to axis 2, consistent ratio that our species really likes, no matter where we are along that actual gradient for each of these individual environmental axes. That's really weird. But what's actually going on here is that these are kernel density estimates, right? And so we've got high density here, and then we've got this tail that sort of leads off in that direction, and that direction, that direction, that direction. And that's the same that's done here, right? You've got this high density here, and you've got these tails that sort of taper off, right? So the thing is, these tails, there may not be any actual data there. These tails are actually specified by the kernel function that's being estimated, and this is just sort of the tapering edge of that kernel. But the weird thing that happens is, you've got a very low number here for the chlorocyanus density. You've got a low number here for the environmental density. But if you just get your kernel set a little bit wrong, this number could actually be very small, which can lead to a really weird thing. So what happens when you divide by a really small number, less than 1, so a really, really small fraction or decimal? Well, it's essentially multiplying by a really large number, right? So if this kernel tapers off before this kernel does, you're dividing a smallish number by an extremely small number, which gives you actually an extremely big number. And so you end up sometimes with this, apparently best possible habitat being in an area of environment space where you have no data, and it's driven entirely by the artifacts of how you've set these two kernels. So it's really worth visualizing these things and making sure you've got something reasonable. I mean, I think that's true of all species distribution modeling stuff. We really need to do more visualization, but in this case, there's a specific artifact that you can be on the lookout for. Okay, so above and beyond there, Ecospat has its own ways of doing the kind of permutations that sort of like E&M Tools does, but conceptually, they are quite similar to what's going on with the E&M Tools hypothesis test. It's primarily this different way of measuring niche overlap, that measuring niches and niche overlap that that is the different thing. So we'll do some Ecospat tests later. Rangebreak tests. So this is the last thing I'm going to talk about. This is something that Rich Glore and I came up with, and we designed these for a specific biological question. It's cool that other people have found places where they can use them, though. So we had this situation, primarily Rich had this situation, where we had these two species, Anolis celestinus and Anolis chlorocyanus, and they're in Hispaniola, and they're on opposite sides of this biogeographic boundary called Merton's line. So there's one anole up here, one anole down here. They meet a little bit in this kind of central area here, but you can see, actually just eyeballing it, I don't know what environmental variable this is. There's this line of red, it sort of goes mostly along the line there, where these two species meet. And the reason that's there is because there's a big valley there. So you've got this area where these two species ranges meet, and it happens to be topographically and environmentally quite different from the area on either side. And so you might want to ask, is the location of this biogeographic boundary set by this sort of environmental barrier here, or is it simply a historical accident? So there's different things you can ask. So one is to say, hey, maybe the habitat north of this boundary is fundamentally different from the habitat south of this boundary. And these two species couldn't live in each other's habitat if they tried. That's one possibility. Another possibility is that everything up here is pretty much like everything down there, and that both these species could live in both places, but there's some sort of ecological incumbency that keeps one from invading the range of the other and vice versa. Or you can have the hypothesis, again, that this contact zone represents an environmentally unusual set of conditions that neither of the species are particularly good at dispersing through. And we had some reason to think that was the case because while one of the species does live sometimes in this area, it's primarily in areas of anthropogenic disturbance, right? These microhabitats around houses and stuff like that are nothing like the surrounding areas. Okay, so we either have some sort of line here that delineates a phase shift in what the environment looks like, or we have this ribbon of unsuitable habitat that's sort of keeping the species apart. So we invented this thing called the linear range break test to test that first hypothesis, that these two regions are just super different from each other, and one species could not possibly live in another species' place. And the way we do this is we take our species, our occurrence points for species A, our occurrence points for species B, we pool them all together, and then we start just randomly throwing lines across the landscape in such a way that we preserve the sample size for the two species. And so we can ask, if we do that, we build species distribution models and measure overlap between them, we could say, okay, what is the expected overlap across a randomly drawn linear barrier across the island of Hispaniola? And then we can compare our empirical overlap to that and say, okay, are the differences between these two species more or less than you expect compared to a randomly drawn linear barrier across Hispaniola? To address the second question, we have what we call the ribbon range break test, where we say, okay, we've got some points in here. Are those points different from the points outside on both sides of the barrier, and are they more different than you'd expect for a randomly drawn ribbon barrier? And so we essentially throw ribbons of a fixed width across Hispaniola, and we say, for all these ribbons, how different is the habitat inside the ribbon from the habitat outside of the ribbon, given the actual occurrence points of our species inside and outside of the ribbon? And then we can compare that to our real ribbon and essentially say, hey, is this super weird habitat? So it's worth mentioning, I've had a colleague or two give me some level of grief over the fact that this only works for very linear situations. So it only works for, where the barrier is linear and where the two ranges are actually not particularly linear. So you kind of need big blobby ranges with a linear boundary between them. Otherwise, there's just not enough ways to randomize the barrier that actually keeps the sample size constant. So if the geography isn't agreeable to this, you can end up with a bunch of, we'll throw this in air quotes, a bunch of pseudo-replicates that are actually essentially the same barrier over and over and over again, and that's not a very good test. So we came up with a different version called the blob version, which doesn't actually require the barrier to be linear. And the blob version basically says, okay, so we take one point, we expand outward from it to get the sort of nearest points, and we say, this is one species, and everything outside of it's another species, right? And so this allows us to essentially do this kind of test in places where we can't actually use a linear barrier and get a reasonable number of pseudo-replicates. Another thing to note is that we could do the ribbon test in our case specifically because we had occurrence points for one of our species inside of that ribbon. And that was actually quite helpful to us because those are what we use to essentially get the environmental distribution of our species inside of that region that we were interested in. If you have a ribbon barrier like that you think might be interesting that your species does not occur in, it is tempting to think you can just randomly sample points from inside that ribbon and just use those. And I think that might be defensible. I'm not sure I've seen it done. Yeah, I'm a little unsure on that one. Yeah. It is, sorry, going back to that issue with randomizing linear barriers, it's a very good idea to visually inspect your replicates, the distribution of barriers for your replicates for these range break tests, particularly the linear and ribbon ones, because if you keep getting the same division of your data over and over and over again, it's going to really screw things up, and that definitely can happen.